So today we are going to do electron configuration and photoelectron spectroscopy. For this video, you're definitely going to need a periodic table. So make sure you grab one of those, and then of course just something to write with and something to write on. Let's get started. This video should be mostly review and with just maybe a few new concepts for some of y'all. So we're going to just go ahead and jump right on in. So electron configuration is essentially the arrangement, let me get down to the highlighter, is the arrangement of electrons in an atom. It's just a way that we can represent where our electrons are in our atom, what the different parts and where those electrons are most likely to be located. But electrons are crazy, so that's a whole nother discussion. But I always think of it as like we're taking a census or finding the address of the electrons in an atom. All right, and there's kind of four aspects to our electron configuration, and depending on what type of electron configuration, it may or may not be represented. So we're going to start with our first one, and our first one is our energy level. All right, so far there are 7 energy levels discovered where electrons can be located. Typically, they follow the row number on the periodic table, with the exception of our D block and our F block. Those do not follow their row on the periodic table, but S and P do. So no, that's not super helpful. One thing to note, guys, is just as our N gets better, so energy level just represented by N, basically it means it's higher energy, it's a larger orbital because it's further away, it's expanding as we go out, it's farther from the nucleus, and it can hold increasing numbers of electrons. So like, for example, the first energy level can only hold 2 electrons, whereas the second can hold 8, and then the third can hold 18, and so on. It keeps increasing. Okay, so the first thing is just the energy level. What energy levels is it on? How far away is it from the nucleus is kind of what that says. Then the next part is our sublevel. And our sublevel is the shape of the region. Basically, it's kind of the area in which electrons are likely to be found. Sublevels are labeled by the letters S, P, D, and F. So our S sublevel is 1 orbital and it holds 2 electrons. It's a spherical shape, so S spherical. The electrons that are like on our periodic table, the S is groups 1 and 2. That's where our S electrons are. All right, and then P is 3 orbitals, holds 6 electrons. It's peanut or dumbbell shaped. All right, so our P orbital is groups 13 through 18. I'm just going to write the numbers from here on out. Our D is 5 orbitals, holds 10 electrons. It's daisy shaped, and that is group 3 through 12, our transition metals. And then finally, our F is 7 orbitals, holds 14 electrons, and that is our lanthanide and actinide series. At the bottom of our periodic table. All right, so there's our sublevels. There's kind of pictures of what our sublevels look like, so you guys can see, here's our S is our spherical, P is kind of that peanut shape, D looks like a flower, and then F is just a fancy, funky, whatever you want to call it. It's just a weird shape, okay? Then we have orbitals. Each sublevel contains orbitals, and that's basically just a region that's high probability for finding electrons. And each orbital can only hold 2 electrons. All right, and then finally, spin. Electrons within an orbital must have opposite spin so that they can overcome their repulsion. And we represent it with opposite arrows. So spin is either like positive 1/2 up spin or negative 1/2 down spin. Okay, cool. Okay, guys, so we're going to go through some definitions now of these some different words to kind of help us in electron configurations. So the first one is paramagnetic. And in a paramagnetic, it has at least one unpaired electron in our orbital diagram. And that causes it to be attracted to a magnetic field. It also causes our transition metals to be colored compounds. So like if I have sodium chloride, which is just table salt, it's white, right? But cobalt chloride, on the other hand, is like a bright red. And so those unpaired electrons cause them to like have those crazy colors, which is just kind of a fun fact. All right, our next one is diamagnetic, and that is that all electrons are paired in the orbital diagram. Next word we have is isoelectronic. So iso, if you guys were in my class last year, you probably definitely know this, but iso means same. So isoelectronic means that they have the same electron configuration and therefore the same number of electrons. So isoelectronic, same electron configuration. If I asked you what's the highest energy amount of electrons or which electrons have the highest energy, those are always the ones written last in the configuration. So we'll talk about filling order, but the Aufbau principle says that we always fill from lowest energy to highest energy. So whatever electrons we end up with at the end, those are our highest energy electrons. Whereas our valence electrons are electrons on the highest energy level. So valence electrons are our outermost electrons, so they would have the highest energy level then. Core electrons is just all the energy electrons. Basically, everything that's not an valence electron is a core electron. Ground state configuration is normal. It's where our electrons are supposed to be, whereas excited state is when our electrons get excited and jump up to a higher energy level. That's when they emit light. If you guys remember from last year, electrons are chilling at ground state, they get excited, jump up to a higher energy level, and when they fall back down, they emit light. So that's where you might have one in a higher energy level where your lower energy levels aren't full. Okay. So let's talk about our rules, our different types of, and then we'll talk about types of electron configurations. We'll do a little bit of practice. All right. So first one is Aufbau's rule, and it just says orbitals are always filled from the lowest energy level out. So we always go from low to high. And Aufbau is actually a German word, and I do believe that it means kind of in some connotations that it means to build. So for Aufbaus, like we're going from highest or lowest to highest. We're kind of building. So we have to build that like bottom layer of those lower energy electrons, fill those lower energies before we can move up. So kind of a fun fact for you. And then our next one is Pauli's exclusion principle. And Pauli's exclusion principle just says two electrons will never have the same quantum number. So electrons must have opposite spins in the same orbital. So basically what that means for us is that if our electrons are in the same orbital, one is going to have one spin and the other will have the opposite spin. So you'll have one arrow up, one arrow down. It really only matters in orbital diagrams. And then last but not least, orbitals of a cell level will fill one electron first and then add a second so that they are maximizing their unpaired electrons and minimizing that repulsion. Because remember, negative things, they repulse each other. So if I was going to draw that one, it would kind of look like this, where I have 3 unpaired electrons, and only after I have 3 unpaired electrons like that, then I can pair them. Yeah? All right. I'm going to go through our types of electron configurations with you guys really quickly, and then I will go through these practice problems. All right? So I'm going to zoom in pretty far because I didn't really give myself space for this, but that's okay. All right, so our first type of electron configuration is just kind of like our normal one. So oops, let me make that a little smaller so it's easier to read. So electron configuration, if I can spell. And in just our normal electron configuration, our energy level sublevel, and number of electrons is represented in our normal electron configuration. Then we have our abbreviated, or you guys may also know it as noble gas configuration. And in this one, basically we just use the previous noble gas to abbreviate and continue from there. And then finally, our last one is our orbital notation. And in our orbital notation, it shows it all. It has our energy level, our sublevel, the orbitals, and spin. All right. So there you go. There's kind of our three types of configurations, just our normal electron configuration, abbreviated or noble gas, and our orbital notation. Okay, we're going to talk about a few exceptions really quickly, and then after we've talked about those, we will get started on doing a little bit of practice. All right, so our first exception is group 6, and these are in our transition metals. So it's those elements right there. Basically, these are going to move an electron from our S sublevel to our D sublevel. This gives a half full D sublevel, which is just a little more stable. So if I was just normally writing the configuration for these, and I'm just going to write a very generic configuration, my very generic normal configuration would be whatever our energy level is, S2, and then, D4. All right. So whatever your energy levels are, that's what those X's represent. Now, in our, what it actually happens is that one of these electrons in my S sublevel moves into my D sublevel. So what I end up with is XS1, XD5. All right. It just moves to our D sublevel because it just makes it more stable. And then something very similar happens down here with group 11, those elements right there. All right. Again, they're going to move an electron from the S sublevel to the D sublevel. That makes the D sublevel full, which makes it more stable. All right. So again, I'll kind of write a very generic for you. So they are normally XS2, XD9. But again, one of those electrons from the S sublevel is going to move to our D sublevel. So that leaves us with XS1, XD10 is what's going on. All right. Okay. That's a lot of basics, and most of it should be stuff that you guys have learned from last year. So hopefully it's not totally new. So now we are going to jump in to doing some electron configurations. So we are going to start with calcium. And the first thing I notice about this calcium is that it has a positive 2 charge. So that positive 2 charge tells me that it has lost 2 electrons. All right, so already we kind of got a fun thing here. So if we've lost 2 electrons, calcium is right here on my periodic table. I don't know if y'all can see that, but it's in group 4 right there, number 20. So calcium normally has 20 electrons, but if it's lost 2, that means it has 18. So that means we're going to be writing our configuration for 18 electrons, which is argon. We'll talk about that in a minute too. All right, I'm going to zoom in really close because I am actually going to write all 3 different configurations for calcium. So I'm going to write kind of small, but I'll zoom in for y'all so that you can see. All right, so first things first, starting with calcium, we, with really kind of argon, because again, it only has 18 electrons. All right, so we start from the beginning of our periodic table, and I always say we read left to right, top to bottom, just like you're reading a book. So we're going left to right, top to bottom until we get to argon. All right, so, argon. So 1s2, 2s2, 2p6, and then 3s2, 3p6. That would be 18 electrons right there. Argon. That's where we got to. All right, so that's our first type of configuration. That's just our normal electron configuration. Then we can also use noble gas configuration. So this is just a normal electron config. Now I'm going to do the abbreviated. So with our abbreviated, we go to our last passed gas, so our last noble gas. So we are writing the configuration for argon here. So that means our last passed gas is neon. So I'm going to put that in brackets. And again, guys, argon is not the reason we can't, I know we're technically kind of writing, I know it's calcium positive too, but since it's lost 2 electrons, it's argon. But this is not our last pass gas because this is where we're ending. So our last pass gas would be neon. So you always have to go to the previous noble gas, even if you're writing a configuration for a noble gas. All right, but then instead of starting at the beginning of our periodic table, we're just going to start with neon. So everything before neon, 3s2, 3p6. And then I'm going to do orbital as well, but I am going to do... No, I'll do full. I thought about doing abbreviated orbital configuration, and you can do noble gas orbital configuration, but I will do the full one for you guys. All right, so 1s has 2 electrons, so 1 would go up, 1 would go down. And then we have our 2s, and again, 1 electron would go up, 1 electron would go down. Our 2p. All right, it's got 6 electrons. Each orbital fills with 1 electron, and then a second electron is added to it because of our Pauli exclusion principle there. Or Hund's rule. Hund's rule, but they have opposite spins because of Pauli exclusion's principle. And then we have our 3s orbital and our 3p orbital. There we go. So there's our 3 different kinds of configurations. And I'm not going to do all 3 for every single element here, but just, for this one, I thought I would show you guys all 3 since it's been probably a hot second since you've done electron configurations. All right, and then for this one, we have the question, what is this isoelectronic with, if any? So what does this have the same number of electrons and same configuration as? Well, hopefully by now you guys know it is argon. Because it only has 18 electrons, it's going to be isoelectronic with argon because it's going to have the same number of electrons as argon. There you go. All right, I'm going to do 2 with you guys, and then I'm going to leave the last 2 to you. All right, so I'm going to do bromine. All right, and I'm going to write full configuration for this one and abbreviated for the next one. Okay, so bromine is number 35 right there on my periodic table. All right, and I'm going to start at the beginning again. So I'm going to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, guys, and at this point, now I'm right here, and so I'm about to enter my d orbital. And guys, you may remember, or you may not remember, our d orbital is always 1 energy level lower than the orbital we're on. So if I'm on the 4s here, that means that this is going to be 1 energy level lower. So that is my 3d. 3d, and then counter electrons across it. 3d10. And then finally, last but not least, 4p. And I go across 1, 2, 3, 4, 5. So 4p5. All right, and I'm going to do uranium. Like I said, guys, I'm going to do the noble gas for this one because it's pretty long configuration. If you don't, I don't really, let's be real. No one wants to have to write that long. So I'm going to do noble gas here. All right, so uranium is right here to my actinoids, guys. So really it's here so it's down here in this one, but really, guys, that's inserted right here in our periodic table. The only reason it's pulled out is because otherwise it wouldn't fit on a piece of paper. That's really the reason. That's it. So exciting. All right, so it's really in this row right here. So if I'm going to do my noble gas configuration, I need to go to my last pass gas, which is right here, radon. All right, so I'm going to start with radon, Rn. All right, and then I'm going to start at the beginning. So my first one would be 7s2, and then I'm going to go down. So 7s2, and I'm down here. And guys, the F sublevel is 2 energy levels lower than the row. So this is the 7th row. So that means this is 5F, and then count across to uranium. 1, 2, 3, 4. So 5F4. Okay. You guys go ahead and try to do gold and platinum on your own. Guys, just a little trick. Gold is one of your exceptions, so make sure you check those exception rules before you answer. All right, so go ahead and pause the video right now. Try to complete those, and when you come back, I will go over the answers with you guys really quickly. Okay, so I wrote out my full configuration for gold, and then I just did, for gold, so talking is hard, guys. So for gold, I wrote out the full electron configuration and the abbreviated electron configuration. Where platinum, I just wrote out the abbreviated because it's really long to write the full thing. So there's my full configuration for gold. I'm just going to give you guys my abbreviated one. So it's XE, it's our last pass gas, 6s1, 4f14, 5d10. So remember, this is one where an electron moves from the s orbital into the d, so that we have a full d sublevel and lose that one there. And then for platinum, our last pass gas is xenon, 6s2, 4f14, 5d8. All right. Hopefully you guys got those. Yeah. Now then, we're going to go into our last little bit, which is photoelectron spectroscopy, or PES. Basically, what happens in photoelectron spectroscopy is they shoot really high energy photons at like pieces of metal or whatever, causes them to eject their electrons. They're able to see how much energy it takes to eject those electrons. So we get this like really cool graphical representation of where our electrons are. So basically, it measures the amount of electrons emitted and how much energy it takes for them to emit them. So this basically helps us to determine the electron structure of an atom, which is like really helpful if we don't know the identity of the atom. So I'm going to show you guys a couple things on these, and then we'll go through these questions, make sure they make sense for you guys. So first thing is over here is this is our relative number of electrons on the y-axis of our graph. And then down here at the bottom, all right, we have our energy. So I do want you guys to make sure you pay attention because your scale won't always be the same on your energy. It may sometimes be flipped or whatever. But guys, over here, you'll notice we have like really high energy, whereas over on the left, we have really low energy. All right, and that can actually be useful to tell us what we are looking at here is based on that energy. So if you guys remember back when you talked about periodic trends, I think just last week, so hopefully it's still kind of fresh on your brain, but when you guys talked about periodic trends, you talked about ionization energy, or how much energy it takes to lose an electron. So the energy it takes to emit those electrons can actually tell us which ones are closer to the nucleus and which ones are further, or which ones take more energy basically to be emitted. So here, the higher the energy is going to be electrons that are closer to the nucleus. Whereas lower energy aren't held as tightly, so these are going to be further from the nucleus. Okay. So I typically like to kind of think through then, what am I looking at here? All right, well, if this one's closest to the nucleus, that's probably my 1s, all right? And then my peak looks like it has about 2 electrons, so 1s2. All right, then logically what comes next? This would be 2s, same height, so 2s2. And then finally, right here, our last one would be R2P, and it looks like it has 1, 2, 3, 4, 5, 6. So 2P6 there. All right. So then our questions over there are like Y and Z represent which sublevels? Well, they represent the S sublevel. And then X is which one? It's our P sublevel. Why is X 3 times larger than Y and Z? Because there's 3 times the electrons. So our P sublevel holds 6, while our S only holds 2. What element does it represent? So we would do our configuration art in our periodic table. So 1s2, 2s2, 2p6 leaves us with neon. And then it says, why does Z have the highest energy? Because it's held closest to the nucleus. The closer you are to the nucleus, the more highly it is held. All right? Hopefully that made sense. Now we are going to do this one. All right, and again, we have to check our scale. So over here, we have a really high energy over here. So again, that's going to be closer to our nucleus, whereas over here is going to be further away. Because the closer it is to your nucleus, again, thinking about that ionization energy, the more tightly held your electrons are going to be, so the more energy it's going to take to get them to eject. So I always like to just kind of write my configuration on top, just going based on my periodic table before I answer any of the questions about these. So for this one, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So after I've written my configuration, it makes it much easier to answer my questions. So number 1 says how many different energy levels are represented. So that would be 4, because I have 1, 2, 3, 4. And then how many different sublevels are represented. So it's S, P, D, and F. I only have S and P here, so I only have 2 different sublevels. And then it wants to know our last question is, what element does this represent? So let's look at our periodic table. So we end up at 4s2. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, ending right there on element 20. And so this element is calcium. All right. So guys, I want you guys to try to do our next one. All right, so I want you guys, again, go ahead and pause this video and then try to go through the questions on the next one. Write out your configuration first and then go through it, okay? Okay, guys, hopefully that wasn't too tricky for you. I know this one was a little trickier with these peaks back here. So those last 2 peaks might have been kind of a little bit throwing you off. Hopefully it wasn't terrible. But our last 2 peaks, if we look at our periodic table, guys, we kind of knew after we filled 3p6 that what was going to be next was 4s2. But looking at our peaks and kind of our relative heights of our other peaks, it really only makes sense for that X to be our 4s2 and not that Y, because we know it has 2 electrons in it. Guys, kind of the reason it's like that, and that our 4s, even though we know that we fill from lowest to highest energy, is because while yes, we fill our 4s first because it's easier to fill, our electrons in our 3d orbital actually have less energy. It actually takes less energy for them they have less energy because they're on that 3rd energy level instead of that 4th. So that's why they are there. So kind of our questions here, how many energy levels are represented? 4. How many different types of sublevels? We have 3. We have our S, P, and D in this one. This element is scandium. X represents our 4s, and then Y represents 3d. And then X does have less energy to remove an electron. Okay. Last one, guys. This one I pulled from actually an FRQ. It's only one part of the FRQ, but I did still pull it. Guys, what I want you to notice about this one versus the other one is that on this one, look over here, this is actually our higher energy. So that one's actually going to be closest to our nucleus. Well, that's our lower energy. So that one's actually going to be further away from our nucleus. All right, guys, so let's kind of look at this. So if this one is higher energy, so closer to our nucleus, so maybe that's going to be 1s2. Then we have 2s2. Guys, just based on our peak right here, that's going to be 2p. And then, we have 1, 2, and then 1, 2, 3. So we have 2p3 there. All right, and then, so identifying our element, that is going to be nitrogen. Okay, guys, as always, feel free to email either Mr. Oglesby or myself if you have any questions at all about this video.